Any questions? Okay, so most of the questions in the exams will be just straightforward questions. I mean, you should be able to do some straightforward computation with what we have done. Maybe one question that will be, I would say, difficult. Maybe. Okay, so today, if you don't have any questions, I would like to continue with the density matrix. Now, if you remember, we had defined this density matrix. In fact, we had started from the wave function. If we expand it in any basis, psi k being the any basis in the Hilbert space, we had seen that the same information is contained in this, the density matrix whose an element is given by a m star a n. So whatever we do with psi, we can do this with this rho matrix. For example, if you have any operator, or you would, if you want to calculate its expectation value, this is the same thing as taking the trace of the matrix O and the matrix representation of this operator O multiply with the matrix representation of the density matrix rho. Furthermore, what we had done was if we calculated rho dot, the time derivative of rho, it was given by the commutator of the Hamiltonian with rho, and in fact, if rho dot is equal to 0, my system is not changing in time. It just implies that Hamiltonian and rho, they have to commute, which implies that in the energy basis, rho can be diagonalized. And in the energy basis, rho and m would be just some rho n, Kronecker delta and m. And then from this point on, we can just use whatever we did before. So rho n is the probability. Oh, sorry, I made some jumps over here. Okay, so psi is given by, if psi is given by this quantity, this is rho, which can also be written as psi. So if you have the wave function, then there's a corresponding rho which contains basically the same information. But rho is more general in the sense that even if the system doesn't have its own wave function, we can still talk about the density matrix of the system. In that case, of course, rho will be, we can write the rho as if my system is in the state psi k with probability pk, then this is my rho. So in this case, my system doesn't have a given wave function. For example, we looked at this example of two-spin systems. If we are looking at only one spin, that spin doesn't have its own wave function. The whole system has its wave function, but I can still define this rho. And in that particular case that we looked at, my single spin was spin up with probability 1/2 and spin down with probability 1/2. And so I can just talk about that rho. And whatever property I'm interested in, whatever I want to calculate about my system, that rho contains all the information. I don't need to know what the rest of the system is. In this sense, rho is more general, so it also allows us to study systems in contact with what we call the heat reservoir. In that case, we don't need to know anything about the heat reservoir. It's just a general system. And I can still talk about the density matrix of my system, and I can work with it. And as usual, we had this rho. Okay, now we have our system in equilibrium. That rho is diagonal in energy basis. So what are these rho n's? Rho n's is the probability that the system, or if you like, you just pick up a system randomly in the ensemble. It's the probability that that system will be in the state psi. Now, in general, of course, if you go to another basis, even if it's diagonal in the energy basis, it won't be diagonal. So if you go make a change of basis, let's say from psi n to phi n, rho in the phi n basis rho n m will be related to rho in the psi basis. With the, well, let me just call these primes. Suppose that phi n can be written in terms of the psi n basis as bn psi n and remember rho was pk psi k, or let's say rho is rho n psi n. Well, let me write it the other way around for simplicity. This is psi this is phi. So if you just use this expansion over there, this part becomes n l b m star b l rho n phi l phi m. So rho in this phi basis and ml element is no longer diagonal, but it is given by bm star bl rho n. Did I forget anything else? Yeah. So what did I forget? What am I doing wrong? Oh, sorry. This is n l. So this is n prime. So B's are the expansion coefficients. B and M is the expansion coefficient of psi n. Well, in general, this will be this won't be diagonal. But for example, when we were looking at in classical case, we said that okay, we always talked about the microstates. We didn't choose a particular definition of the microstates for any given description of the microstates. Well, in classical physics, we usually use the microstates as position and the momentum, but that is not necessary. I mean, we didn't discuss it much, but in phase space, if you just make any canonical transformation, the phase space volume doesn't change. So you can just use whatever you want to describe your microstates. Well, if you want the same thing over here, we already see that the rho is diagonal in the energy basis. You can still ask it to be diagonal in any basis, but that doesn't kind of come automatically because you see here, this is in general not diagonal. But you can make an assumption, random phase, which is the random phase approximation, or assumption, let's say. You see, if you look at these terms, as you change n, This is a complex number. This is another complex number. In general, their phases will be unrelated to each other. And so you get, here you have a bunch of complex numbers, not necessarily random, but almost random. Some of them will have positive phases between 0 and pi over 2. Some of them will have phases larger than 90 degrees, larger than 180, etc. So you do expect some cancellation. Now, this random phase approximation tells us that the approximation is exact unless, you see here, if you look at these terms, this will be in general sum over n, b and m, b and l, e to the power I phi and l minus phi ml rho n and m, no, this is n l and l. So you have all those random phases as you are summing over n. So unless L and M are equal, you expect some cancellation in general. Need not be exact, but you do expect some cancellation. Now this assumption basically tells us that unless L and M are equal, the cancellation is exact. That's just an assumption. It doesn't have to work all the time. It seems to work. So this just says that this sum is equal to 0 if L is not equal to M. When L is equal to M, there's no phase over there. So it's just rho n is a positive number. That absolute value is a positive number. So you're just summing positive numbers. So with this assumption, rho ml, also in this new phase is rho m, let's say, whatever it is in this new phase, Kronecker delta ml. It's also diagonal.
We basically said that B complex and B conjugate and B is equal to 1. We try to force them
No.
equal to 1. So
No.
That we have a value.
No, we didn't force them to anything. In fact, they can be anything. But what we are assuming here is that, you see, that phase, it will have general values. So if we just imagine this as summing complex numbers, summing some numbers in the complex plane, you see, if this is your complex plane, one of them will be this, the other one will be this, the other one might be this one, this is some other number. So this is in general what you end up having. Some will be large, some will be small, but in general you will get some cancellation. This is for Lm is not equal to L. The cancellation need not be exact, but still there will be some cancellation in general. The assumption tells us that that cancellation is exact. That is the assumption. I'm not assuming these to be anything. You see here, the size of these arrows in the complex plane will be determined by both these and also by rho. As I said, some of them will be long, some of them will be short, but when I sum them up, they will cancel some of them. Other questions? So let's do some examples with this density matrix.
I did this.
Hmm?
I did
We will do it, but not the first example that we will do. That will be the second one. That will be the third one. There is an even simpler system. Spin in a magnetic field. Well, the Hamiltonian is easy. Minus mu b, the Bohr magneton, times the magnetic field times sigma z. Then we can use any representation. Sigma z, we can take it to be diagonal. Then remember rho in the microcanonical ensemble. No, in the canonical ensemble, rho was just e to the power minus beta h divided by trace of e to the power minus beta h. Well, the exponent of minus beta h is exponent of beta mu b times b times sigma z. Well, this is something, well, the exponent or the arbitrary functions of matrices are defined in terms of their components, in terms of their Taylor expansion of the function. Well, sigma z is diagonal, so this is easy to carry out. To calculate, this is exponent of beta mu b times b, the 1, element, 0, 0, exponent of minus beta mu b times b.
But as long as it's not single, we can always put it in that position. Exponentials of matrices, matrices of exponentials with this symmetric transformation. We can always find, even if it's not diagonal,
well, okay, so let's just make an interlude. If you have some function and you want to calculate the matrix element, you want to calculate this function for that matrix. This will be the Taylor expansion, 1 over n factorial, the nth derivative of n at 0, m to the power n, and from 0 to infinity, assuming f is analytical, its Taylor expansion exists, etc. If m is diagonal, f1, f2, f whatever, if it's an n by n matrix, then the f of m will be quite easy to evaluate. It will be a diagonal matrix with entries of f of f1, f of f2, f of f3, f of fn, fi being the eigenvalues. If m is not diagonal, but can be diagonalized, you see, this is now it also depends on how you diagonalize it. It can be diagonalized by a unitary matrix. Well, orthogonal matrix, you can say that it's a special case of a unitary matrix. In that case, M will be U, some diagonal matrix, lambda 1, lambda n, U dagger. Or let's say, if what can be diagonalized by let me say U inverse. The crucial thing is one is U, the other one is U inverse. You have to make that choice. Otherwise, it doesn't work. Well, in that case, for example, M squared becomes U, the diagonal matrix, U inverse U, diagonal matrix, U inverse, which is U, this is just one, diagonal matrix, squared, a diagonal matrix of lambda 1 squared lambda n squared times U inverse. Well, you can in fact generalize it. M to the n will be U diagonal matrix lambda 1 to the n lambda capital N to the n U inverse. So f of m will be U diagonal matrix f of lambda 1 f of lambda n times U inverse. So it's crucial that these two matrices, when multiplied, gives the identity matrix. Okay, so this is already diagonal. So taking the exponent is kind of trivial. So its trace is just exponent beta mu b times b plus exponent minus beta mu b times b, which is twice the cosine hyperbolic. So we know the density matrix. Let's calculate the average energy, which is the average of the Hamiltonian, which we know is given by the trace of the Hamiltonian times rho. Remember, Hamiltonian is given by this matrix over here. So trace of Hamiltonian times rho is mu b times b minus mu b times b divided by twice cosine hyperbolic beta mu b times b. This is the overall factor. If you multiply the matrices, the first row doesn't change. The second row gets a sign. So the average of the Hamiltonian is minus mu b times b divided by twice cosine hyperbolic beta mu b times b. If you just take the trace, it gives you twice sine hyperbolic beta mu b times b. 2's cancel, we get minus mu b times b sine hyperbolic divided by cosine hyperbolic. Yeah, which was the result we had obtained before. So again, here you can see that if the average energy of the system is positive, beta has to be negative. So we have all this discussion about the negative temperatures, etc. Any questions? Now let's look at the ideal gas. Let's look at one particle. First, we need to identify the energy eigenstates. The Hamiltonian of the system will be minus h bar squared over 2m times the Laplacian. The wave functions corresponding to a given energy. Well, I will use the periodic boundary conditions. X plus L, Y, Z is equal to phi E, X, Y plus L, Z, X, Y, Z plus L. So if you just move by L in any direction, it should repeat itself. The wave functions just turn out to be 1 over L to the power 3 halves e to the power I k times R, with k being 2 pi over L nx, ny, and z. These are our wave functions. We know what, okay, so let's calculate e to the power minus beta times the Hamiltonian. Let's calculate let's calculate it in position space. What is this matrix element? Well, the easiest way would be just to insert a complete set of energy eigenstates. Which will give us sum over all possible nx, ny, and nz's e to the power minus beta. Hamiltonian will be just k squared over 2m divided by L cubed times R phi E of R prime. But remember, this is what we call phi E at the position R. This is the conjugate of phi E at the location R prime. So this matrix element of this operator will be summed over nx, ny, and z e to the power minus beta k squared over 2m divided by L cubed phi E of R, phi E conjugate of R prime. We know that what phi E is, this one. So this is equal to sum over nx and y and z e to the power minus beta k squared over 2m divided by L cubed e to the power I k R minus R prime. I just substituted the wave functions up to this point. Now the next thing will be I will convert this to integration. This is approximately equal to, let's say, d cubed n divided by L cubed e to the power minus beta k squared over 2m e to the power I k dot R minus R prime. And I know what k is. K is 2 pi over L times n, or n is L over 2 pi times k. So the energy is h bar squared k squared over 2m. So here I have an h bar squared. So this is equal to d cubed k divided by 2 pi cubed, e to power minus beta h bar squared k squared over 2m e to power I k r minus r prime. Now let's evaluate that k integral. I will go to spherical coordinates, dk k squared d theta, no, d cosine theta, d phi. Cosine theta goes from minus 1 to 1, d5 goes from 0 to 2, of e to the power minus beta h bar squared k squared over 2m divided by 2 pi cubed times e to the power I k r minus r prime times cosine theta. Now I chose my coordinates in k space such that kz points in the direction of r minus r prime. So theta is the angle that k vector makes with r minus r prime, and phi is just how much it rotates around that axis. So phi integral is trivial, that is 2 pi divided by 2 pi cubed. We have dk k squared e to power minus beta h bar squared k squared over 2m from 0 to infinity. And then I have a theta integral. Well, the cosine theta integral just gives e to power I k r minus r prime divided by k I k r minus r prime cosine theta goes from minus 1 to 1. This is equal to 1 over 2 pi squared, 0 to infinity, dk, one of the k's cancel. There's a 1 over I, so that makes a minus I over here. And e to power minus beta h bar squared k squared over 2m e to power I k r minus r prime minus e to power minus I k r minus r prime. Divided by r minus r prime. Okay, I can still simplify this integral a bit further, minus I over 2 pi squared dk k e to power minus beta h bar squared k squared over 2m plus I k r minus r prime from minus infinity to infinity. The integral from minus infinity to 0 just corresponds to the second term. So what is this integral? Well, first of all, we have oh, sorry. How do we evaluate that integral? Well, let's just carry it out. This is minus I over 2 pi squared, 1 over r minus r prime. Well, I don't want this k, so let me first get rid of that one. Or 2m plus ik times alpha. I need to take the derivative with respect to alpha. That brings an ik. So let me also, this is minus 1 over 2 pi squared. So this is the same integral. dk. Now this is a Gaussian integral. You can just complete it to squares, and then you can show that it is actually pi squared over beta h bar squared over 2m squared. This is what you would have obtained if that alpha term was absent. When you make the shifts, etc., this you get e to power minus alpha squared divided by beta 4 beta h bar squared over 2m. And remember, alpha is equal to r minus r prime. We first take the derivative with respect to alpha, then just substitute alpha is equal to r minus r prime. So this is minus 1 over 2 pi squared, 1 over r minus r prime. So here I have 4m squared pi squared divided by beta squared h bar to the 4. And then that derivative, oh sorry, there is no square. This is under square root, so there is only one of them. It's a one-dimensional Gaussian integral. So that is square root of 2m pi divided by beta h bar squared. And if I take the derivative with respect to alpha, that brings a minus alpha over twice beta h bar squared times m e to power minus alpha squared divided by twice beta h bar squared, alpha squared up. Okay, when I use alpha is equal to r minus r prime, this alpha cancels this one. This minus sign is cancelled by this minus sign, and we have 1 over 2 pi squared, square root of 2m pi over beta h bar squared times m over 2 beta h bar squared, exponent of minus m r minus r prime squared divided by twice beta h bar squared, if I didn't make any mistake. So any questions up to here? Well, it's just quantum mechanics plus some algebra. So let's obtain the row. Remember, row matrix is e to power minus beta h divided by the trace of e to power minus beta h. Now the trace of e to power minus beta h is actually d cubed r prime. And this is equal to d cubed r. When r is equal to r prime in the matrix element of e to power minus beta h, the exponent just becomes 1. We are left with all the these coefficients. So it doesn't depend on R, so the R integral just gives us V. And
we directly write the trace term, and then from the dr cube integral, write a drag delta and take the drag delta inside with K. Would that be faster to take this integral? If we directly write the trace term, we also have the R integral. And on the upwards, we have IK R minus R prime. And
where? Here, you mean?
We also have one for R minus R prime. Okay.
Hmm? Yes. It's the diagonal element. It's not R prime. So traces, take the diagonal element, sum over them. Here I'm using the position basis to calculate it. So I just write the matrix element in R, and then summing over R is just integration over R. You can use the momentum basis if you like. You can use the energy basis. In fact, if you use the energy basis, you will get an expression which seems very difficult to sum. Basically, this is the sum. And finally, rho R prime is just 1 over V times the exponent of minus m R minus R prime squared divided by twice beta H bar squared. In particular, if you look at some diagonal elements, so this is just 1 over V. Well, this diagonal element tells us the probability that it will be at the position R. In a sense, so this tells us that that probability is constant, the probability density that it will be at the position R, let's say. The probability density is uniform. So in the particle, in the box, our particle can be anywhere with equal probability. Well, that's what we expected, because just a single particle moving freely around. And in fact, that was kind of our starting point. Any microstate is equivalent to the other one. It doesn't depend on the temperature. Let's calculate, for example, the energy, the average energy for the system. Well, the average energy will be trace of rho times h. This is d cubed r rho h, or let me write it the other way around, h rho r. But now I can use the position space representation of h. This is the same thing as d cubed r well, let me write it in this form, minus h bar squared Laplacian divided by 2m r rho r prime, evaluate that r prime is equal to r. And so the reason why I'm doing this is that Laplacian is the derivative of the bra only, not the ket. So this is equal to d cubed r minus h bar squared Laplacian over 2m. Well, that matrix element is given by this expression. which is equal to d cubed r minus h bar squared over 2m times 1 over v minus m over twice beta h bar squared times the Laplacian of r minus r prime, or r minus r prime squared. I don't write the exponential again, because when I set r is equal to r prime, it becomes 1. Now, what is this Laplacian? Okay, these h bar squares cancel, minus signs cancel, m factors cancel, and I'm left with 1 over 4 beta v.
Shouldn't that be power to the equation and over 2 beta h bar squared?
Yes, 2 is over there. Just 2.
No, that has to be power 2.
Why?
We're taking Laplace in the second derivative, so
Oh, okay, so I probably shouldn't take any shortcuts. Well, that term will be 0 when r is equal to r prime. Well, let's see. D cubed r minus h bar squared over 2mv times del over del xi del over del xi exponent minus m xi minus xi prime squared divided by twice beta h bar squared. Evaluate that r is equal to r prime. This is equal to d cubed r minus h bar squared over 2mv, derivative with respect to xi of minus m over twice beta h bar squared times twice, let me put a j over here, twice xi minus xi prime times the exponent. Everything evaluated at r is equal to r prime, which will be equal to, okay, these m's cancel, h bar squares cancel, I will have minus signs cancel, d cubed r, 1 over 4 beta v, now these two cancels, one of these two, so I have the derivative of xi minus xi prime, which will give me 3. Remember, I'm summing over I. Derivative of xi with respect to xi for 1i is 1. I'm summing over 3 possible values of I, so that is why I have 3, and that's it. I don't write the other term because the next term will be xi minus xi prime times the derivative of the exponent, but when I set r is equal to r prime, xi minus xi prime will be 0. Well, this is 3 over 2 kt, d cubed r just gives me v. Let's cancel this one. So this is the average energy. So at least whatever we had obtained before holds in our new formalism. What we have done is consistent. Any questions? So let's give a break now, and in the next hour we will have the harmonic oscillator.